Good afternoon, everyone. I hope you had a good weekend. Now, last week we talked a lot about sound waves. This week we're going to turn our attention primarily to how light acts like a wave. So we know that waves, in general, travel according to the equation v equals f lambda, where v is our speed, f is our frequency, and lambda is our wavelength. Now, for light in vacuum, or in air to 2 or 3 sig figs, so in vacuum or air, the speed that light travels at is going to be c, the speed of light, which is about 3.0 times 10 to the 8 meters per second. So that's the speed of light in air or in vacuum. Light travels slightly slower in air than it does in vacuum, but to 2 sig figs, the number is the same. But what happens if our light is traveling instead through water or through a glass prism? Well, it turns out that our light is actually going to slow down when it hits other materials. So we have what's called the index of refraction, and we'll talk a little bit later today about what refraction means. But for right now, all you need to know about the index of refraction is that it's a property of a material. So it's a constant for a given material, and we use the letter n to denote it. So this is our index of refraction. And it's just the ratio between the speed of light in vacuum and the speed of material. So it's defined as c over v, where c is speed in vacuum, and v is our speed in material. And so basically what our index of refraction tells us is how much does our light slow down when it's in material. If n is really big, that means that v is proportionally really small compared to c. And if n is very close to 1, that means that our light is traveling at very close to the speed of light in vacuum. So are there any questions on this? All right. So one thing to be aware of is that our frequency is a property of the light wave that does not change. So our speed changes when we hit a material, but our frequency doesn't change. So I'm just going to write that on the board. Now, I know we're not doing quizzes anymore. This used to be a typical quiz question that Mr. Douche would give, is to have you do a problem and ask how the frequency changes when the material changes. And the trick would be the frequency doesn't change, but that may very well show up on the final exam. So just be aware that if he's asking you about how the frequency changes in materials, the frequency doesn't change. So the frequency is a property of the light that remains unchanged. So F stays the same. In materials. So if it goes from air to water to glass to, any number of transitions, F is always going to be the same. But what doesn't stay the same is our wavelength, because we know that V equals lambda F. If V changes and F doesn't, then that means lambda also has to change. So if we look at our equation, so I'm just rearranging V equals lambda F. So it's lambda equals V over F. And so we want to know, how does our wavelength change when we go into a material? So I'm just going to give us a little subscript MAT for material. Now recall that we have n is equal to c over lambda, c over v from earlier. So I'm just going to solve this equation out for v. So I'm going to multiply both sides by v and divide by n. We're going to get that v is equal to c over n. So let's call this equation 1 and this one equation 2. I'm just going to take this right here and substitute it into equation 1. So we're going to sub 2 into 1. And what are we going to get? Well, we're going to have lambda in material is equal to, now we're going to put C over N in place of V. So we're going to have C over N, that whole thing divided by our frequency F. Well, this is the same thing as C over N times 1 over F, so we can rewrite this as C over F N. Now let's factor out 1 over N. So we're going to have 1 over N times C over F. Now what is C over F? We know that our wavelength is V over F, and if we're traveling at the speed c, that's going to be our wavelength in vacuum. So C over F is the wavelength in vacuum. So we're going to have 1 over N times lambda vacuum. So as our final statement of our equation, we will have that our wavelength in material is going to be equal to our wavelength in vacuum divided by our index of refraction. So are there any questions on this? All right, so let's do an example. So let's suppose we have a green light and we shine it into a bucket of water. Now our green light, let's suppose, has a wavelength of 520 nanometers. So our wavelength in vacuum of our green light is 520 nanometers. And our bucket of water is at room temperature, so it has an index of refraction of 1.33. So our first question we want to know is, what will the wavelength be in water? Well, we just learned how our light changes a material. So we're going to have that lambda, and instead of saying sub MAT, I'm just going to use sub WATER, because it's water we're working with. So lambda sub water is going to be equal to our wavelength in vacuum divided by our index of refraction. So our wavelength in excuse me, our wavelength in vacuum is 520 nanometers. Now I'm going to go ahead and convert this to meters. In this particular instance, it doesn't matter if we leave it in nanometers or convert to meters, but there will be things later on in this lecture where it's going to matter that we convert to meters, so just for consistency, I'm going to convert this one as well. So we're going to have 5.20 times 10 to the minus 7 meters divided by 1.33. So our wavelength is going to turn out to be about 3.9 times 10 to the minus 7 meters, or if we want to talk about it in nanometers, it would be 390 nanometers. So that's how our wavelength would change when it goes from air to water. Next thing we may want to know is, all right, well, our wavelength has changed. What color is our light now? Now this one's kind of a trick question. So 390 nanometers, that's about the wavelength of red light, I think. But if you take a green light bulb and you shine it into water, you'll notice that its color doesn't change. So if you just take like a green flashlight or something and you just point it into the water, you're still going to have green light. So what's going on? Well, when they say that green light has a wavelength of 520 nanometers, or red light has a wavelength of, blah, blah, blah nanometers. They're talking about the wavelength in air. Frequency is the defining characteristic here. So the frequency didn't change, and so the color won't change. So when you have light, it has a certain frequency. That frequency is what determines the color, not the wavelength. So even though our wavelength changed, our color will still be the same because the frequency is still the same. So our light is still green. So are there any questions on that? All right, well, we may also want to know what speed is our light traveling at now that it's in water. So that's going to be the last part of this question. Well, to figure out the speed, we're going to go back to our index of refraction equation. So we know that n is equal to c over v. So I'm going to multiply both sides by v and divide by n. And we're going to get that the speed is equal to c over n, which is going to be 3.0 times 10 to the 8th meters per second, divided by 1.33, which would give us 2.26 times 10 to the 8th meters per second, or since we only use 2 sig figs here, our speed will be 2.3 times 10 to the 8 meters per second. So are there any questions on this example? All right, so next we're going to move on to double slit interference. So let's suppose we have a laser. And I'll use, well, green's a laser color too. We'll use green for our laser for now. And so we have a laser, and we shine it at a double slit. And so all a double slit is like a little device that has two very tiny, very closely spaced slits in it. So kind of a zoomed in picture of our double slit. It would look something like this. These two lines here would represent the slits. And so we have our laser light. It's going to come through, pass through our slits, and there's going to be some screen back here. And so if you were to guess what kind of pattern our light would have on the screen, probably your initial instinct would be that we're going to get kind of these two big green lines. And that's kind of our gut instinct. But it turns out that's not actually what happens. So if we want to see what actually happens, I'm going to share our screen for a second. So for grad lab, I did the double slit experiment. And so this picture on the left is what happens when you have light passing through just one slit on its own. And you can see you get kind of a big block of red light like what you would expect. Now, if you look closely, you can see these other little red fringes off to the sides. And we'll talk later in the week about why those appear. But you can see it's mostly just like this one big red block. But the picture on the right, that shows you what's happening with the double slit. And instead of having two distinct red blocks, we have, red region, a black region, a red region, a black region, red, black, black. And it just kind of alternates. We have all these little red, black regions all across this. So it's not at all like what we might expect. So why does this happen? Well, to understand this, it's helpful to think about light as spherical waves. And just as a reminder, our double slits have to be really small for this to work, but I'm going to draw it really big so you can see it. So This kind of like if we turn the slit on its side, or if we're looking at maybe a top-down view, we're going to have a slit, and there's going to be separation space, and then we have our other slit. Now our light is going to come through in spherical waves. So we're going to have some light coming through like this, and like this, and like this. And you're going to get these spherical wave fronts. And the same thing is going to happen to the other slit. So we're going to have like this, and then like this, and like this, and like this. So if we look at what's happening here, well, if we look at this center line where we had that brightest spot, we can see we have crests lining up with crests. And it's hard to see the troughs because they're somewhere in this white region, but we're going to have troughs lining up with troughs, crests with crests, trough with troughs. So we're going to have our maximum constructive interference right here in the center. So I'm just going to denote that with a bright fringe. So that's what you see on your screen. You're going to see a very bright red spot because we have maximum constructive interference here. Now, what about right here? So at this spot right here, we have a crest and it's meeting a trough. And if we kind of continue down this line, we're going to have another crest meeting a trough. And so we're going to have maximum destructive interference here. So we're not going to have any of our red light getting through. It's just going to be black. No light's getting through. Now if we look over on the other side, it's symmetric. So here we have a crest lining up with a trough, and it's going to continue on down. So we're going to have max destructive interference here. And then if we hop over here, we can see we're going to get the crest lining up with crest pattern again. And troughs lining up with troughs. So we're going to have constructive interference again. And we're going to have the same thing on the other side. And our pattern is just kind of going to alternate for a little bit. And so this spot right in the center is where we're going to have the most interference. And so that's going to be the brightest spot. And we're still going to have some interference over here, but it's going to be a little less bright. And if we were to continue this, would be, to the next bright spot, it would be a little less bright, and so on and so forth. But that's just roughly a conceptual picture of why we have those fringes instead of having, just the kind of the two bright spots like you might expect. So are there any questions on this? All right, so let's look at the math. How can we explain this, or how can we work with a double slit experiment? Well, to start, we're going to draw a picture of our situation. So let's suppose we have our double slit. And we have a screen somewhere out here. And our screen is spaced some distance L away from our double slit. So this L, that's the distance we are from our screen. Now we're going to have a bright spot here. That's going to be our brightest spot. That's our central maximum. Let's suppose we have another bright spot up here somewhere. And so we want to know how high up is this. So we're going to call that height y sub m. We want to know how high is this next bright fringe going to be, or whichever bright fringe it is. And this sub m, we're just using to denote that there are multiple bright fringes. So we call the central maximum the brightest bright spot, the m equals 0. And then the next bright fringe would be m equals 1. The next one after that would be m equals 2, so on and so forth. So you want to find out the location of this one. Well, to do this, let's draw in our lasers. And they're not going to be super important right now, but they will matter later. So I'm just going to draw in our laser light. So our two lasers are going to travel to hit the screen. And you can see that this one's going to have to, the light from this beam is going to have to travel a little bit farther because this line's a little bit longer than this one. Now I'm just going to draw a line kind of going through the center here. And so we're going to call this angle here theta sub m. And so if we want to write an expression for this height using our angle, well, if we look relative to this angle, this is our opposite side, this is our adjacent side. So the trig function we probably want to use here is tangent. We're going to have that tan theta m is equal to, well, our opposite side is ym, our adjacent side is L, so we're going to have equal to ym over L. And we want to know how high up it is, so we're going to solve this expression out for ym. And we're going to have ym is equal to L tan theta m. Now, one problem with using this equation is our angle, it turns out, is going to be really small. Because again, these slits are going to be spaced really, really close together, and our screen is going to be really far away. So we want to find some way to replace the angle in this equation, and to do that, we're going to zoom in real quick on this area here and do a little bit of trig with it. So we're just going to enlarge this region we had here. So zooming in on our double slit, we're going to say the distance between the two slits is d, the separation distance. And let's draw in our light. So we have one laser beam coming through this slit. We have another beam coming through this slit. And let's redraw that center line we had from earlier. So this one's just going between the two. We know that this angle here is theta m. Now, when we zoom in really close like this, these two laser lines are going to look basically parallel. We know they're not exactly parallel, but they're very, very close to parallel. And we're going to be able to use that fact to help us do some math. So, if we draw a straight line going like this distance down here, which I'll color in blue for us, this is going to be our path length distance. So how much farther does this light have to go to reach our screen than this one? So this is delta R. And since all of these lines are parallel, well, this line and the center line and this one, if we draw in this line here, so one that's parallel to this angle has to be theta m as well. So these two are just these true triangles, they have basically this line's the same and this line's the same, so the angle has to be the same. So, well, this right here is a right angle, so if this part's theta m, this remaining bit has to be 90 minus theta m. And so our whole triangle has 180 degrees in it. So that means that this leftover bit has to be theta m. Because then we'll have 90 degrees here, 90 minus theta m, and then theta m, you add those together and you'll get the 180 degrees that you need. So are there any questions up to this point? All right, so now we're going to do a little bit of trig. So if we look at this side here and this length here relative to this angle, so this is our opposite side and this one's our hypotenuse. So opposite of our hypotenuse would be sine, so the expression we want to write is going to be sine. And we're going to have that sine of theta m is equal to, our opposite side is delta r over d. So if we want to go ahead and solve that out for delta r, we're just going to multiply both sides by d. And we'll get that delta r is equal to d sine theta m. Now, if we think back to last week, we learned that for waves, constructive interference happens when we have an integer multiple of our wavelengths. So when delta r is equal to m lambda. So since this is an expression for delta r and this is an expression for delta r, we can just set the two equations equal to each other. So we're going to have m lambda is equal to d sine theta m. Now I'm just going to divide both sides by d to solve out for sine theta m. We'll have sine theta m is equal to m lambda over d. Now, at first pass, this equation may not seem very useful, because our ultimate goal is still to figure out what our height is for our bright fringe, and that equation has tangent in it, not sine in it. So why did we take all this trouble to solve out for sine? Well, recall that our angle has to be really small. And so when we have a really small angle, we can use what's called the small angle approximation. And so the small angle approximation tells us that sine theta is approximately equal to tan theta. Now the reason why this is so tangent is sine over cosine. And if your angle is very small, it's very close to 0, cosine is going to be very close to 1. So you'll have what's approximately sine theta divided by 1, so tangent is going to be very close to sine theta. So we're going to be able to replace the sine in this equation with tan theta m is equal to m lambda over d. So now we're almost done. All you have to do is go back to the equation we developed earlier for our height y sub m and plug in our values and we'll be there. So we had y sub m is equal to L tangent theta m, which is going to be L times m lambda over d. So you will end up with y sub m is equal to m lambda L over d. And this is for constructive interference. Our bright fringes. Now we might also want to find the location of our dark fringes. The math for this is almost identical, so we're not going to do the full derivation. But recall that for destructive interference we have, so I'll write destructive, instead of having delta r equals m lambda, we're going to have delta r equals m plus 1/2 lambda. So in that step where we set the two delta r's equal to each other, we're just going to have a different delta r on one side of the equation. And so if you go ahead and crunch the numbers, you're going to get that for destructive interference, you'll have our dark fringes y sub m, and we're going to give a little prime just to denote that now we're talking about the dark fringes, is equal to m plus 1/2 lambda L over D. So the equations look very similar. The only difference is instead of having m, we're going to have m plus 1/2. So are there any questions on this? All right, so let's do an example. So let's suppose that we have a green laser which has wavelength of 500 nanometers or 520 nanometers. And we're going to shine it through a double slit, and our two slits are spaced 1.0 times 10 to the minus 4 meters apart. So the separation distance is going to be 1.0 times 10 to the minus 4 meters. And now our double slit is located half a meter from our screen. So the distance between our double slit and our screen is L, and that's 0.50 meters. We want to know how far from the central maximum is the next bright fringe. So let's draw a picture real quick so we can see what we're talking about. So we have our double slit, we have our screen, and so we're going to have a bright fringe right here. This would be our m equals 0 bright fringe. That's the central maximum. We want to know how far away is the next brightest fringe. So we're going to go one up from our central maximum. So that's going to be m equals 1. So we want to know what's the height of the m equals 1 bright fringe. So all we have to do is get out our equation that we derived earlier and plug in our values. So we're going to have y sub 1 equals m lambda L over D. Well, m is 1. Lambda, now here it matters that it's in nanometers. We need to convert to meters because we're going to have this in meters and this in meters as well. So it will be in our best interest to convert this into meters as well. So we're going to have 5.20 times 10 to the minus 7 meters. Now our length we said was 0.50 meters. And we're going to divide through by our separation distance, so 1.0 times 10 to the minus 4 meters. So if we plug this into our calculator, we're going to get that y sub 1 is equal to 0.0026 meters to 2 sig figs. So are there any questions on this example? All right. So the last concept we're going to focus on today is reflection and refraction. Now this is actually from chapter 18, but it's what your lab is on this week. So we're going to go through what reflection and refraction are because it's going to be helpful for you in lab. So sometimes it's helpful to think about light as waves, and that's what we're doing most of this week. But sometimes it's also helpful to think about light as rays. And the ray notion of light you're probably familiar with. It's the idea of light traveling as a beam. Maybe it's a beam going through a prism or something like that. And so when we're talking about reflection and refraction, instead of thinking about light as a wave, we're going to think about it as a ray. So when you have light and it interacts with a surface, there are two things that can happen. The light can be reflected, as in it can bounce off, or it can be transmitted, also known as refracted, which means it passes through the material. So we'll talk about reflection first. And reflection is probably something you're fairly familiar with. So let's suppose we have a mirror. And we have a flashlight. And this is an experiment you can actually try at home. If you go into your bathroom, you turn off the light, and you hold the flashlight up and shine it into the mirror, you're going to see light that appears behind your head on the wall. And if you change the angle, the height on the wall where the light appears is going to change. So let's suppose I'm holding a flashlight and I shine it into my mirror, and it hits the mirror here. And so it's going to have some angle. And when we're talking about reflection and refraction, the relevant angle is the angle between the surface normal and our beam. So I'm going to draw in our surface normal. And we're going to call this angle theta sub I, which means the incident angle. It's just the angle, the incoming angle, the angle at which the light is coming in through. So this is theta sub I. The light's going to hit the mirror, and it's going to bounce off. We're going to call this angle theta sub R, so it's reflected. And for when we have reflection, theta sub I equals theta sub R. So the angle that it's bouncing off at is the same as the angle that it came in with. And so, again, theta I is our incident angle. And theta sub R is our angle of reflection. Now, what about refraction? If you've ever seen light go through a prism, or if you've seen the way light bends when it hits the water, then you've seen refraction firsthand. So what happens with refraction is something like this. So let's suppose we have a glass prism. And so up here we have air, and then down here is our glass prism. And so we have our light. It's going to come in. And we're going to draw our surface normal again, because again our angles are defined with respect to the surface normal. So we have some incoming angle, theta sub I, and there are two things that the light can do. So some of the light may be reflected. That's one possibility. But some of the light may be transmitted, so it may go through the material. You may get a picture that looks like this. Now the tricky thing about refraction or transmission is that the angle is going to change. So when the light passes through into the material, we're no longer going to have the same angle we had before. So how can we relate our two angles? Well, they're related through what's called Snell's law. So Snell's law tells us that if you look at n sub I sine theta sub I, that's going to be equal to n sub t sine theta sub t. Now theta sub I is our angle of incidence, and theta sub t is our angle of refraction. So and the n's are just the respective indices of refraction. So n is an index of refraction. So n sub I would be the index of refraction for our incoming material. So if we're in air, the index of refraction is very close to 1. And for all our calculations we're going to do in this class, we can use 1. I think it's like 1.0003. So since you only need 2 or 3 sig figs, you're going to be fine using 1.0 or 1.00. And then if we have water or glass, it would be 1.3 something for our transmitted one. So in lab this week, what you're going to be doing is you're going to have a simulation tool where you will have a digital light beam, like a virtual light beam, and you can change the angle. And you're going to be measuring, they have a little protractor that you're going to plop down on your, this is all of course happening through the computer, so it's just a simulation program. They're going to give you a protractor, and you just change the angle of the incident beam, and your refracted beam's angle is going to change as well. Now if you just were to plot theta sub I versus theta sub t, you're going to get something that looks really weird and it looks like it's not related at all. You're going to have a hard time fitting it with a graph. But if you plot sine theta sub I against sine theta sub t, you're going to have something that looks a lot more sensible. So after you collect your data in lab, whether it's today or tomorrow, the thing you're going to want to do is you're going to want to take the sine of those angles, and that's what you're going to want to plot opposite each other. So are there any questions on that? Are there any questions on anything we've covered today? All right, if there are no further questions, that's all I have for you for today, so have a great day.